How can chaos theory be used in developing new medicines? Every fall, we hear news about flu vaccines. This type of flu is likely to spread this winter. Because of these predictions, we can be prepared. However, even when predictions seem convincing, we sometimes still get the flu after getting the vaccine. If the virus changes even a little, and if our movement and contact change even slightly, the outbreak curve can take a completely different shape. What matters here is that we did not fail to predict because it was random, but because small differences can grow much larger over time. In mathematics, we call this chaos. Chaos is not the absence of order, but what happens when very small changes lead to large differences. Nature shows us patterns, but it does not always remain the same. In the 1960s, Edward Lorenz was studying a weather model when he noticed something unusual. Only a few decimal places in the starting numbers were different, but over time, the forecast took a completely different path. On the surface, things may seem unpredictable, but underneath, there is still an order. That order does not move in a straight line, but along a winding path, which makes prediction more difficult. This idea becomes even more real in medicine. Our body is not a simple machine. Hormones, the immune system, nerves, and metabolism are constantly interacting with one another. A medicine works in this network by changing how these parts work together. The problem is that our bodies do not always respond in proportion. Sometimes a very small change can cause a large reaction, while at other times, the same stimulus causes almost no change. This is where chaos theory becomes helpful in developing new medicines. Instead of searching for one average response, we pay attention to the points where reactions change suddenly. For example, when we increase the dose just a little, the effect can suddenly become much stronger, or side effects can rise quickly at a certain point. At these points, we cannot simply think, "This will be fine." When we notice these tipping points, the way we develop the medicine changes. A dose that is safe for some people can be risky for others. Because of this, researchers no longer dismiss signals such as heart rhythms or brain waves as mere noise. In a healthy body, these rhythms vary slightly. Researchers pay attention to how complex these changes are, how the patterns shift over time, and how the rhythms change when illness begins. If we can measure these differences reliably, we can notice much earlier where a new medicine may start to cause problems. Now something becomes clear. To understand how our body responds, we look to biology. To describe these changes in numbers, we use mathematics. To see how patterns shift over time, we turn to physics. To make sense of it all through real data, we rely on information science. When chaos theory is applied in medicine, it does not involve a single theory crossing into another field. Many fields are working on the same problem together. There are clear limits. Medical data is often irregular, and people respond in very different ways. Chaos analysis does not automatically lead to treatment. For now, chaos theory in medicine is not a final answer, but more like a sign pointing to where the path begins to split. The development of new medicines becomes more precise when predictions begin to fail.